right, section 8.8 is the last in chapter 8. So we're going to just kind of finish up the chapter by talking about remainders and error in Taylor polynomial estimations. So we talked about this particular concept in the last section, and this concept is just the concept of a remainder. So the remainder in general is when you take an approximate value, when you are estimating an exact value and we say it's equal to the approximate plus the remainder, okay? So if you were to rewrite this equation solving for the remainder, that would mean that the remainder is equal to the function value minus the estimation value. So remainder is a value that has a sign, a positive or negative sign to it. And if we want to use remainder to find the error value would just be the absolute value of your remainder. So error in general is just a positive number, where remainder can have a positive or negative sign to it. Here's a visual to go with that concept. So this black line represents some function called f of x, and the dotted blue line represents the Taylor polynomial created to model or estimate that function. And the Taylor polynomial was centered at this dot here that we're calling C. We are using the Taylor polynomial to estimate the black line at the value a. And obviously it's not the same as the y value on the function, but the y value on the Taylor polynomial is pretty darn close. The difference between those two y values is what we call the error or the remainder. So what we're going to be doing today is working on solving, finding the exact error in a Taylor polynomial and finding the remainders in the Taylor polynomial. So we're going to use Taylor's theorem to help us do that. And Taylor's theorem says that basically if you have a function that's equal to a Taylor polynomial, which all of this here is just a Taylor polynomial, then that Taylor polynomial plus the leftover stuff, which we call the remainder, is equal to the function. Okay, now the remainder has, it is possible to compute that remainder, and the remainder is computed by taking one term beyond where your Taylor polynomial stops. So we would change and say, like, if our Taylor polynomial stops at n, we would change and call it n plus 1. That means one term past where you are now, over n plus 1 factorial times x minus c to the n plus 1 power. Okay, a couple things about how we're going to use this. We have two rules that will help us find an upper bound for the error. An upper bound means that that's the most that your error could be. So this is not us computing the exact error all the time. This is just saying that your error will definitely be at most this much, and that just gives you some more information about your estimation. So two situations. If you have an alternating series, the error will be no greater than the absolute value of the first unused term. Okay, so we'll see an example of that in the notes. Scenario number 2, if you have a non-alternating series, you will approximate it using Taylor's inequality theorem, also called the Lagrange form of the remainder, also called the Lagrange error, different names for it, but here's what that looks like. So we're actually going to start with that. So in the Lagrange form of the remainder, essentially for a non-alternating series, instead of stating what the next term would be, we will say what the maximum value of that term could be, and we'll use that to help us determine the remainder. Okay, so this maximum value may or may not be given. We're going to look at 3 different problems, some where it's given and some where it is not. The vocab is something we'll do at the end, so I want to just get to some examples. I feel like if we do a couple practice problems, then the vocab will make a little bit more sense. So let's start with something you know, and that is to write a third degree Taylor polynomial centered at x equals 3. So this is just review of the last lesson. So looks like it would be 5, because that's the first value, plus, that is the wrong number, 2, plus 2 times x minus 3 to the first power. Negative 4 is my next value. That would be times x minus 3 squared. So hopefully all of this is looking familiar because this is something that you had to do in lesson 8.7. Use this to approximate f of 3.2. So remember that your Taylor polynomial models or estimates your function. So if I want to find f of 3.2, I can use the Taylor polynomial to do that by plugging in 3.2. So in the parentheses, I would have 0.2 if I subtract. And I'm just kind of simplifying a little bit. That way, when I get to the point where I'm ready to type into a calculator, I'm not typing in as much. So I'm just simplifying the things that are easy to simplify, okay? So this is what it would look like simplified a little. And we're getting, I'm not going to round too much, 5.329 if, oh, it does say 3 decimal places, 329. Part B is where we're going to start something new, okay? So it says the fourth derivative of f satisfies the inequality that f to the fourth, oh my lord, the fourth derivative of f at a of x minus 3 to the fourth power of fourth factorial is less than or equal to 35. So this number here, they're referring to this as the maximum value, okay? The maximum value. And use this information to find a bound for the error found in A. So we're going to use the Lagrange error formula. I'm going to be really detailed in how I write these notes, okay? So I would say the remainder for a third degree polynomial, because that's the one we just wrote, will be computed by looking at the next term. Actually, let's write it as the maximum. You can write this a couple different ways. I'm going to write it as the maximum of the next term. So 4 factorial x minus 3 to the fourth power. Okay, now that maximum value is 35 per the information given in this problem. So we are going to change that to a 35. Okay, so we've created a little remainder / error formula. Now we're going to evaluate by plugging in 3.2. Okay, the polynomial, by the way, this is the center value of the polynomial, and this is the value that you're estimating at. So 3.2 is what you are plugging in. So you're going to use your error formula, and you're going to plug in 3.2 in place of x, which would give you 0.2 in the parentheses. And then you're going to go to your calculator for it to do the rest. So the calculator should tell you 0.00233. That is your error, okay? The error means that is how far off your estimation could be. Our estimation currently is 5.329. It could be 0.00233 larger than that, or 0.00233 smaller than that value. So this is how much you are off, okay? Sometimes we call this the error margin. It's like the statistical term for that. Margin of error. So part C, find an interval such that A to B is basically like the lower bound and the upper bound of what your answers could be. So you're going to take your estimation, which was 5.329, and you are going to add the error, and then you're also going to subtract the error. So my lower bound would be 5.329 minus the 0.00233. That would be 5.327. That's the lowest that my answer could be based on possible error. And if I add the 0.00233, I would get 5.332, which means that's the largest that my possible answer could be. D and E are going to require the use of answer C, in that we're asking if answers are possible or not. So could f of 3.2 equal 5.311? Well, f of 3.2 can equal anything in this interval, okay? So 5.311 is in the interval, so then yes, this could equal 5.311 because that number is in the interval. Okay, what about 5.334? That's a no. 5.334 is larger than the biggest number in the interval, so we would just say something like it's 5.334 is not in the interval. All right, so that example was an example of a how to compute an error when the maximum value is given. Example 2 is how to compute your error when the maximum value is not given. Okay, so let's start with what do we know? We know that we're estimating sine of 0.5. Okay, so that means we will need to find the remainder. I don't know the degree of my Taylor polynomial that I'm using because it says what is the degree. So I'm going to have to circle back to that in a minute. And then we are doing also a Maclaurin series, which means we are centered at 0. So I'm going to set up my little formula. For this one, I don't know the value of n, so I am unable to put the number down here needed for the factorial. So it's just going to have to be n plus 1 for now. And then the same thing for the exponent attached to x. I don't know what the value of n, the correct value is, because it's not given here. So for now, it's just going to have to be an x to the n plus 1. Okay, so our goal next is to figure out how we find this value. So the way that we will do that is we will think about the function sine. And actually, we're going to think about the absolute value of the function sine. So maybe start to ask yourself, what is the maximum value of sine? Well, the maximum value of sine is 1. And I need a maximum value for this problem. So 1 is going to be the number that we use in place of m, because the max that sine could be is 1. Now I realize this top number usually represents a derivative of your function. But what's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. So the derivative of sine is cos, and cos is sine, and it just keeps going back and forth. Well, the derivative, if it were cosine, the maximum value of cosine is also 1. So we could just safely say that the maximum value of either sine or its derivative will always be 1. So 1 is the number that we will be using. All right, so I guess I can plug in now. I'm going to plug in 0.5 for x, and I'm also going to plug in 1 for the m value. Okay, so I have this. Now, if you read the question again, it says, what is the least degree of the polynomial that assures an error smaller than 0.001? So I want this answer to be smaller than 0.001. The issue is I don't know the correct value of n that will give me that. And there's not a nice way to do this other than just guess and check. So what I like to do is make a table, and I'm going to kind of set up what I'm doing in this table. So what I'm going to be doing is I'm going to be plugging in values of n until I find a value that is smaller than the error requested. So I'm going to start with the value 2. I'm not starting with 1 because that would mean the first term works, which is probably never going to happen. So I'm going to start with 2. And again, I'm just plugging this value in for n. So that would make it 0.5 to the 3rd power over 3 factorial. You will grab a calculator to help you with the rest. And this is the answer that you get. Is this number smaller than the error margin? It is not. So you're going to keep going. And we are looking for the smallest value of n that would work here. So you don't want to start with too big of a number for n because that might give you an error that's within the range you want, but it might not be the least value. So the next one would be 0.00260. That also does not work because this is larger than the error that we are looking for. And so it's just a repetitive, a little bit of a tedious process, but nothing too hard because you're doing the majority of the work in your calculator. Here's what happens when n is 4. We get 0.00026. That is smaller than the error margin, meaning if n was 4, then that would give me an estimation that's accurate to 0.001. Okay, so we're going to say, therefore, n equals 4 is the least degree needed to be accurate to 0.001. Okay, so that is an example of how to find your error value when the maximum is not given, but also when you're looking for the value of n. Here's the third type of problem. The third type of problem says, let P sub 3 be a 3rd degree Maclaurin polynomial for f. Using information from the graph of the 4th derivative, show that P sub 3 minus f is less than 1 over 400. Well, this whole thing here is just the equation for how to find the error. Okay, the estimation minus the actual value is what we call the error, or the absolute value of the remainder. So that's what they're asking us to do when they write it that way. So let's start with writing the rest of the formula to find this value. So we're looking for the maximum value over the next term would be 4 factorial over x minus 4, not 4, goodness sake, it's a Maclaurin polynomial, so it's x minus 0, but x to the 4th power. And we want this to be, they want us to prove that it's less than 1 over 400. All right. So kind of like number 2, the last example, this value is not known. Okay, and actually I think maybe I'll write it a different way to show you what I mean. Remember that top number represents, in this case, the 4th derivative at the value of 0 because it's a Maclaurin polynomial. Okay, I actually can use the graph to find this value. This value is on the graph. It says f4 of 0, which means the 4th derivative, which is what this graph is. When x is 0, that looks to me like it is at 15. So we're going to call it 15 divided by 4 factorial times x to the 4th power. We want it to be less than 1 over 400. Okay? Next, you're going to plug in your estimation value, which is 1/4. Now I'm choosing to simplify a little bit as I go. 1/4 to the 4th power would be 1/4 to the 4th power. And I need to figure out what this would be equal to as a fraction, which I think, let's see, 15 over 4 factorial times 4 to the 4th. I don't know. Let me see if I have it written down here. Yes, it would simplify. You can divide and simplify, but it's eventually going to reduce to 5 over 2048. Now, you can, of course, use a calculator to help you with this, but 5 over 2048 is equal to 0.00244, and 1 over 400 is 0.0025, okay? By the way, we're asking a question here, like, is this actually less than 1 over 400? And here in this last step, we can confirm that, yes, it is less. So basically, your work is done. You have shown that the answer is true. Okay. It says here, just a quick note, if an error calculation is required on the AP exam, all work must be shown, so the calculator can only be used as a method to check your computations. So you have to essentially show your work. You know, we all kind of know that that's how AP rolls. So let's look at example 4, and I'll show you what kind of work needs to be shown. Use the Maclaurin series for y equals e to the x to estimate 1 over radical e accurate to 4 decimal places. Okay, let's start with something simple. 1 over radical e is the same as e to the negative 1/2 power, right? So essentially, we're going to use e to the x, and we're going to plug in negative 1/2 for that. Now, a while ago, I told you guys that it's probably smart to memorize some of the more common Taylor and Maclaurin series, like e to the x, sine and cosine, and ln. And this is an exact, perfect example of why we want to memorize those. I'm supposed to be analyzing e to the x, and we're going to kind of, if we know the formula, we're going to kind of manipulate it a bit to change it and make it work for e to the negative 1/2 power. Here's how that works. All you have to do is change x to negative 1/2 and then do a little bit of algebra. So if I wanted to write this as in series notation, I could write it as negative 1 to the n times 1/2 to the n over n factorial. And that's just going to tell me how to write the terms for that Taylor series. Okay. Now that we've written it as a series, we should note that this is an alternating series, okay? And in the notes at the beginning, it said for an alternating series, the error will be equal to, so the error is the first unused term in the sequence. So this is a little bit different than what we have just been doing. Alternating series, when we go positive to negative to positive to negative, you will use, to find error, you will use what the first unused term would be. So if you have a 3rd degree Maclaurin series, you would use the 4th degree term, okay? A little bit different than finding that maximum value that we have just been doing in the previous examples. Let me show you how this looks. Okay, so I'm going to set up my remainder work. So it is the remainder. I don't know how many terms are needed. This is a problem where we are going to be trying to figure that out, how many terms are needed. But I know it's going to be within an error bound of the n+1 term. And I'm using this series here to write this part of it. n plus 1. Okay, so similar to what we did with that sign problem earlier, we have to do a guess and check game to figure out what the correct n value would need to be to find an error that's accurate to 4 decimal places. That's the goal this time. Actually, you know what? I'm going to take out the -1 part of it because the absolute value will make that go away. So I need to do guess and check by plugging in different values of n and seeing which one's accurate to 4 decimal places. So I chose to start at 4 this time. There's no reason for that. I just decided that it was probably not a small number because we're looking for a pretty accurate estimation. So I simply just plugged in n equals 4, and the answer I got was 0, 0, 0, 2, missing a 0, 0, 0, 0, 2, 6. That value is not accurate to 4 decimal places because there are still numbers in the 4th decimal place. So you have to keep going and try the next value of n. So the next value of n is 5, which would give me 1/2 to the 6th power over 6 factorial. And that is an answer of 0, 0, 0, 0, 2, 1, 7. This answer is accurate to 4 decimal places because the first 4 decimal places are 0. Meaning if you added this number to a value, the first 4 decimal places would not change because there's nothing in it. So this gives us a value, an n value of 5 needed to produce an accurate solution. Okay, so we need n equals 5. Will produce an accurate solution to 4 decimal places. Okay, one thing real quick, you can actually check your work here. This is where you can go to your calculator and let it help you, okay? It's not a real complicated thing. What you're going to do is you're going to check and see what e to the -1/2 power is equal to, okay? And it is equal to 0.6065306, okay? And then what you're going to do is you're going to see what your Taylor polynomial would equal to n equals 5, so the 5th degree Taylor polynomial, which that would be, I'm going to write out some of the terms of it, but I would need to go back up and look at this guy right here. So I would plug in n equals 0, plug in 1, plug in 2, and so forth until you get to n equals 5. So those terms would look like this. This is just me plugging in n equals 1, n equals 2, and so forth. And then eventually what you'll do is once you have the 5th degree polynomial written out, like what I'm doing right now, is you will type all of this into a calculator as well. And that's going to give you your estimation for the first, for your estimation with the 5th degree Taylor polynomial. And that value is 0.6065104. So if you compare answers to the actual thing and the approximation, they are both the same in the first decimal place and the second and the third and the fourth. The 5th decimal is where it changes, so we can say that this is actually accurate to the first 4 decimals. Okay, I think I'm going to skip this problem and let you try on your own because this one is very similar to the last example. You're just trying to figure out the value of n that will allow cosine to be correct to 6 decimal places. Okay, so I will post an answer key with my work shown for this example. but I would like you to give it a try first.